I think picking up from what we left last time we were talking about the spectroscopy. So we were discussing more like the general principles, the general applications of spectroscopy, and we had demonstrated several examples that we used spectroscopy in the past, including both hard X-ray and soft X-ray. And today it will be more fundamental, and as the title suggests, I'll be talking about, how to understand the many electron system. We may touch this a little bit in the previous lecture, but today we'll go to more details. And I believe this is important because in practical life, all the systems, all the materials we deal with are multi-electron systems. We rarely deal with a single electron system. But in fact, many of the languages we use, or many of the pictures we have in our mind are based on the single or the one electron picture. In a lot of cases, they're valid. And we have no problem using those kind of languages or pictures to communicate. But there are also cases that they're important for understanding their complexities associated with many electrons. So today, I hope I just can give you the impression that the many electron systems, they're unique, have their own unique complexities, but we can understand them to a reasonable degree of clarity, such that we can modify our one electron language and have a better understanding of the systems that we want to understand. Okay, without further ado, I'll just move on to the next. So I'll just first quickly go through the one electron picture and the meaning about the transition metal oxides. And this is I think probably the most common material systems that we encounter in our research. Either the lithium or the sodium cathodes, many of them are based on the transition metal oxides. So I think the general picture is using the crystal field splitting theory, such that the original 3D orbitals, which we described in their spherical symmetry environment, as in the case of the hydrogen, now split. And because of actually their symmetry change, it's no longer spherical, but it's a tetrahedral, it's octahedral, but surely we can also extend that to the tetrahedral as case. So in an octahedral case, the 3D splits into the T2G and EG. This is a typical description of how the 3D electron orbitals split. So we have 5 3D orbitals in the beginning. Now we split into 3 T2G and 2 EG. And also roughly we can estimate the energy decrease and increase associated with such kind of splitting. And to do further, we can even do the electron counting and have estimation of the energy change. For example, let's say if we originally have 3D electrons, have 3 3D electrons, then and all of them go to the T2G, then we can calculate how much energy is lower, right? And this delta CF stands for the energy of a crystal field. So this is something that can be calculated either from the spectra or from the theoretical calculation, sometimes also termed as 10dQ. So with that number, we can calculate how much energy is lower if we have 3 electrons sitting on the T2G. And likewise, if we have, for example, a high spin configuration for the 3D5, so we have 3D electrons on T2G and the 2 electrons on EG. Now we know we have 3 electrons contributing to the lower energy part, right? But also we have 2 electrons contributing to the high energy part. And we can do a simple math by subtracting this part from this part, and we get how much net energy we gain or we lose after adopting this kind of T2G configuration. And to do even further, there's a so-called octahedral site stabilization energy, which compares the energy of this configuration with the energy of T2G with the of the tetrahedral configuration. I didn't draw the picture, so I think probably it's not a good idea for me to go to the details. But in our previous 2016 advanced energy material paper, we were talking about the ion substitution in the spinel, and we discussed that. And that concept is also commonly used by Professor Manthren in UT Austin when he was talking about, why some elements favor the octahedral side while others do not. So those are some of the directions that you can go into details to have more knowledge about this kind of crystal field splitting. This picture is more geometrical, and they're also sometimes very useful when we talk about the different T2G or EG orbitals. For example, in original 3 orbital, now it splits into, this is a set of T2G, and they are dxy, dxz, and dyz, right? And we also have the 2 EG orbitals, which are dx squared minus y squared and d3z squared minus r squared. In particular, if you take this one as example, I think it will help us to easily to associate why the EG is a sigma bonding, because you see this is EG, and this lobes are directly pointing towards the poles, right? So if we have the titanium here, then we have this kind of EG orbital. So they are pointing up and down, and they're pointing directly towards the oxygen. It's kind of head-on interaction, and it's makes sense to characterize them as their sigma bonding. So EG are sigma bonding, and the T2G are pi bonding. You can have a more clear picture by drawing this kind of orbitals yourself. And I think it should not be easy, very difficult to figure out. These 3, they fall into the category of pi bonding, and these 2 fall into the category of a sigma bonding, right? So they are head-on interactions. And also because of that, their EG interactions are stronger than T2G. And also, I need to mention that in most of our oxide systems, transition metal oxide systems, the HOMO level, the highest occupied molecular orbital level, these are the antibonding in nature. So what does that mean? That means that if we have more electrons in the EG, we're weakening the bond because they're antibonding in nature, right? So those are some of the key ideas, key concepts to touch when we talk about their one electron using the framework of the crystal field splitting. And there one extension of the simple crystal field in which we simply regard this kind of ligands as point charges, and now the complexity may rise. What if we have, instead of a spherical anion, we have some kind of a molecule, right? So for example, in the case of the monoxide or in the cyanide, the complexities can rise. And in those cases, a more generalized theory of the ligand field theory can help us to understand those scenarios. And those kind of concepts naturally arise, such as the sigma or pi donor or acceptor. Okay, I have to play with the camera window. Sometimes it's just doesn't want to stay in their should be position. Okay. Somehow I lose everybody. Well, anyway, I need to spend more time on using Zoom. So this is a more extension of the crystal field, which simply regards the ligand as point charges. Now we have a more practical situation where the ligands can be molecules with certain geometrical shapes. I also encourage you to spend some time, maybe not too much, on understanding this. And this is a very useful for the chemistry study, but practically maybe not frequently used for doing the battery research. Okay, not too much time I want to spend on the single electron picture. Now we move on to the many electron picture, which is the one I really want to discuss today. So what we discussed the previous weeks, all talking about the single electron, right? We're talking, we do the electron counting, and we say how many electrons sit on this 2G, assuming that there's no interaction between them or whatever. When we go to the many electron systems, a good starting point, I think, could be the excited helium. And this is maybe the simplest many electron system, right? We have only 2 electrons, and involving very simple orbitals. One is 1s, the other is 2s. So for the helium in the ground state, we have the 2 electrons sitting in the 1s orbital, right? But once it gets excited, and then we have the 1s, 2s. But you probably want to ask why we want to talk about excited helium, because in excited helium, we have several possibilities, right? If it is in the ground state helium, then there's only one possibility that they're paired and they're sitting in the lowest possible orbital, which is 1s. So there's nothing more to talk about. But once we have the excited helium, then we have the possibility of occupying different orbitals, right? So we have the 1s and 2s. And also each electron can adopt a different spin configurations. Could be spin up or could be spin down, right? So in principle, we have, this kind of the total of 4 possibilities for the excited helium state. So this is a good starting point for us to understand the many electron system. But I would remind everybody at the very beginning that as simple as they seem, we have only 2 electrons. The real understanding is not that simple. But still, we can really gain some insightful understanding by going through the derivation of this many electron systems. And I'm also asking a question which seems to be pretty easy here. So we can easily configure their 4 possibilities, but what are the real final states that the excited helium will be staying at? So we have to go back to talk about the wave functions, right? So that's really the place of, that's really how we get the ideas, how we get the really new insight or the new findings about this kind of system. And so everything boils down to the mechanical quantum mechanics. And the essence of quantum mechanics is basically saying we cannot deal electron as just a particles. It's also a wave. So electrons have to be regarded as a wave. And but very amazingly, they can be described quantitatively as wave functions. So I think that should be the pillars of the quantum mechanics, that electrons are waves, and we can describe them using wave functions. So the natural question is then, how do we describe this kind of 2 electron system using the wave functions? Right? So maybe a very easy guess is that, can we simply use the multiplication of both the 1s and the 2s wave function, since we know we can derive the analytical solution to the Schrodinger equation of a hydrogen atom, then we know the exact solution of the 1s orbital and also the 2s orbital. We have the exact mathematical expression of them. So for this kind of a combination of 1s and 2s, can we have something like a simple multiplication of 1s wave function multiplied by the, oh, sorry, I'm sorry, this is a typo here. So this should be 2s, okay. But you guys should know what I mean. Can we simply have this kind of wave function to describe the system? The answer is no. And why the answer is no? Because there's some more intrinsic physics has to come into play here. What we just mentioned is that electrons are waves, right? But we also have to respect the reality, or the big fact that the electrons are fermions. So this may sound something very abstract, that why we just simply want to understand the electron structure. We have to understand something like they're very related to the particle physics, the fermion and the bosons, because this is something that's very intrinsic, that determines the properties of electrons, determine the wave functions, the behavior of wave functions. So that's no way to get around this concept. So what is the fermion? The fermion is simply saying that it's asymmetric upon exchange of the electrons. For example, if we have two electron systems and we exchange them, we change one from two. So if this system is there, these particles are fermion, that's saying the wave function describing the system will be asymmetric, meaning that it will gain a negative sign in front of wave function upon exchange. So this is the what's the definition for fermion? In comparison, the photons, they're bosons. So bosons, they're regardless of the exchange of their particles. If you exchange these two particles, the total the total function will be the same. So there's no negative sign induced. So this is the definition of fermion, and this would have a very far-reaching implication on the form of wave functions. So I hope this is something that can leave a deep impression in our mind that electrons are fermions, and we have to respect this kind of fermion property. And the second thing relates to the Pauli exclusion. I think everybody learned in their college chemistry or other textbooks that Pauli exclusion is simply saying that we cannot find two electrons in the system that have the identical four quantum numbers. The main quantum number, the orbital quantum number, the magnetic orbital quantum number, or the spin quantum number. We just cannot find two electrons that have everything the same, right? They have to be something different. So that's what basically the Pauli exclusion principle is talking about. And thirdly, this something may sound very trivial, but in fact, this is has also had a lot of implications in the practice. It's called indistinguishability. So what is this saying? That we cannot really tell electron A from electron B. There are no different electrons. They are all the same. So, and the corresponding mathematical expression for that is this kind of expression saying that no matter how you exchange the electron, yes, you will change the wave function with a minus sign, right? But don't forget, the real meaningful physical property is the electron density, and electron density is the magnitude of the wave function, right? It's not just the wave function itself; it's actually the square of the magnitude of the wave function. So what I'm saying that if you exchange the two electrons, yes, indeed, because electrons are fermions, you have a negative sign now, but you do not change anything about electron density. The electron density will remain the same upon your exchange the two electrons. So this is something that may sound trivial, but is also indeed very important for constructing the wave function. Okay, so now we know these three requirements, and those three requirements, they probably may be very physical, but they are very practical, meaning that we can no longer really use this kind of a simplification to really construct a wave function that meets the fundamental physics requirement. And that puts some kind of a restrictions on what kind of a wave function form we can have, or we can possibly have, that can be the answer to the question. So based on those requirements, and the people can construct this kind of a wave function. You see, this is a little bit more complicated, right? Instead of using simply the multiplication, we now have actually a linear combination of two possibilities. So this is one stands for the coordinate of the electron 1, and 2 stands for the coordinate of electron 2. So, and A stands for the wave function of 1s, and B stands for the wave function of 2s. So we see that these two terms, they are simply changing the sequence. But now, by using a linear combination of them, right, by subtracting, doing a subtraction among them, we now can construct a wave function that really satisfies the physics requirement for the wave function. So I just repeat again, the three requirements is a fermion, and it should obey the Pauli exclusion, and their they should be indistinguishable. By having this kind of a space wave function, we now satisfy all the physical requirements. So at least we can do something may not be 100% accurate, but at least the physics they make sense physically. Okay, so then we can go ahead. And there are also a little bit more things to add. Is what we just did is in fact for the spatial part. So if you recall the wave function, it only includes the spatial part, right? Describes their electron density distribution in the space. But for electron, it also has a spin part. And this may also be something that is not very easy to understand because we are maybe used to like a plus or minus sign for spin, or there or a plus 1/2 or minus 1/2. Those are very those are simplifications of the real case. So in the real case, the spin part are also described by a spin function. So it is also a function. And the spin function is just like the wave function. The spin function is actually a eigenfunction to the spin operator. So I don't know if you still remember those kind of concepts we mentioned in previous lecture. We talk about operator, we talk about eigenfunctions, right? We talk about the function basis. So we know that all this kind of Schrodinger equation, they're just the eigenfunction problem. So we have an operator. The operator could be a Hamiltonian, including both the potential and the kinetic energies, or it could be also we have the analogy for the spin. And so we have a spin operator. Then we also need to find the eigenfunction for the spin part corresponding to the spin operator. That's too much details, but at least I hope you can accept that the total wave function includes both the spatial part and the spin part. And for the spin part, we can also construct the spin part function using this kind of either the multiplication or the linear combination of them. Now we can use simply multiplication because the spin part do not have those kind of restrictions for the spatial part, right? And this is a very nice lecture series from MIT. I mentioned this also in my previous lecture. It's 561 called Physical Chemistry 1, and it was taught by Professor Robert Field. There are also a series of videos recorded on YouTube, which is free. You can also access those if you have time and interest. In this lecture, it's lecture 22, he had a very detailed mathematical derivation for both the spatial part and the spin part. So this can be regarded as some kind of extended reading if you have time. Okay, now we can construct the total wave function. Like I said, it includes both the spatial part and the spin part. And in the specific case of two-electron system, we can write the whole thing in this kind of a form because if we go to more complicated systems, actually, they cannot be fully separated. But for the two-electron system, and which is also a lucky case that we can write the total wave function in this kind of form, and we can arrive this kind of answers. Don't be bothered by the details of these expressions. We'll directly go to the conclusions we have, right? Let's forget about the mathematical details for the moment. Let's just see what kind of conclusions we can learn from this kind of mathematical expressions. So the first point I would say is we can immediately see spin and the spatial part, they're correlated. What I mean is that if we look at this kind of spin part, right, you will see, so this part is in fact, it's a symmetric. I hope you still remember the definition of a symmetry in the physics. Symmetry simply means something is unchanged upon a certain kind of operation, right? So what we mean by symmetry is that if you change coordinate of sigma 1 and sigma 2, you have the same value. So this whole thing is not changed. So this is a symmetric with regard to the exchange of sigma 1, which is this representing electron. So if you exchange electron, the spin part wave function doesn't change. So it's symmetric. So we see this is symmetric. and this is also symmetric. And this is also symmetric. It's easy to tell. If you change sigma 1 to sigma 2, you can verify that this part is also symmetric. So if you have a symmetric function for the spin part, the consequence is that you remember that the total electron wave function has to be asymmetric upon exchange, right? Because it's a fermion. So if you have this part that is symmetric, then the spatial part has to be asymmetric. So this is what I mean, that there's a correlation between the spin part and the spatial part. If you have a asymmetric spin, then you must have a symmetric spatial function. And vice versa, if you have the symmetric spin part, you must have an asymmetric spatial part to match, such that the total wave function is always asymmetric, right? Everybody agrees? Okay, good. So what that means is actually more far-reaching. So we do not have really to go to even further mathematical derivation, but now we have some kind of a sense. We have some idea that spin really correlates to the spatial distribution, right? Because this special wave function is really the part that describes how the electrons are distributed within the space. But this correlates to the spin. And what that means is spin correlates to the spectrum distribution and also in turn correlates to the energy. Because we know if we have too much electron in a compact space, then we have a lot of repulsion, right? And the energy will actually shoot up. And if we have an electron distributed over a large volume or space, then we do not have too much repulsion, and the energy will be low. So these three terms, they are correlated intrinsically, right? So this is the point one we can get from this kind of answers to the two-electron system. The second thing is diagram is not equal to eigenfunction. I need to explain a little bit more what I mean here. So what I mean by diagram, I mean the electron configurations, right? We have been already custom used to drawing the electron diagrams. So in the case of the T2G EG, we will say, okay, so this is the system. We have the 3 electrons sitting on the 3 T2G orbitals, right? So that's easy to communicate. And to some kind of approximation, they are correct. Then they are faithful to the chemical result to a certain degree. But that's not the real case. Because if you look at these 3 functions, in fact, they do not have a strict correspondence to the electron configuration. In other words, for example, for this wave function, you do not cannot describe, say, oh, this is actually correspond to this space or correspond to that space. No, it's actually a linear combination of these 2 configurations, right? So in the 1 electron world, we draw the diagram like in this way. So we have the spin up, we have the spin down, we have the pair, right? The kind of spin pair. This is the diagram we have been drawing all the time. But in fact, the real wave function is not something corresponding to them. In fact, the real wave function actually corresponds to the linear combination of these 2 configurations. So that's more complexity, right? And that relates to the third point. When we talk about the singlet and the triplet, and probably you already know that for excited helium, we have 2 kind of states. So if you do the spectral, you have observed 2 lines. One corresponds to the singlet, and the other corresponds to the triplet. But the singlet is not something. In fact, simply actually the pair. In fact, it's a combination of this kind of 2 paired configuration. We have spin down, spin up, and spin down and spin up, and there's just a minus sign. I still cannot. I'm still bothered by the position of the camera. Okay. Yeah, I think I also made a mistake here. So this one should be reversed. So this one should be the spin up, and this one should be spin down, right? If these 2 are the same, then the net result will be 0. So there's a mistake here. I hope you understand what I mean. What I really meant is actually this should be spin up, this should be spin down. and just like in these two cases. So the real singlet is actually a subtraction of these two. And another linear combination of these two configurations goes to one of the triplet state, in addition to their speed down pair, the parallel spin, and this kind of two parallel spin configurations, and this linear combination of this the pair spin. And these three are the real triplet states we have. Okay, so maybe before getting you too confused, I just want to re-emphasize the important points. The first thing is, I think we probably all appreciate now is correlation between spin and the spatial, and also the energy. The second part is in the quantum chemistry in the real case, sometimes this kind of a one electron diagram we have been using all the time does not strictly apply, right? So in other words, if you want to understand the spectroscopy, and you just want to understand it by drawing this kind of single electron diagrams, in a lot of cases, actually you'll fail. You will not be able to correlate what you draw here to what you observe in the spectrum, because we know spectrum corresponds to the states, right? So that's the main point I want to convey here. And we can go further and to learn from the results. And let's just still forget about the mathematical details and accept that we can derive the energy by this kind of integration, right? So we have the Hamiltonian, and now we have the wave function, as we shown in the previous slide. And now once we do the integration, we can calculate the energy of this kind of systems. And also, like in the previous case, the detailed mathematical derivation is also in Professor Robert Field's lecture notes. The real important conclusion is here, is what I put in the red bracket. The energy, the system of energy corresponds to long interacting energy, meaning that we have those electrons pretending that they simply ignore the presence of each other, right? They simply behave independently. It doesn't really care who's around. So that goes into the non-interaction energy, but there's still energy there because we have the nuclear, right? The nuclear is attracting the new electrons. So there's still potential energy there. And also we have additional term arising from the interactions of the electrons. And if we do the integration of the interactions, then we realize this can be further divided into two parts. One is called Coulombic interaction. And this is easy to understand. We know electrons, they have charges. So as the particles bearing the same charge, they're supposed to repel each other, right? So we have the Coulombic interaction with repulsion, and that will increase the energy. But this term is pure quantum mechanical and doesn't really have an analogy in the classical world, right? This is called exchange interaction. What this exchange interaction means that once these two electrons, they have the parallel spin, actually there's some extra energy associated with that. So, and in fact, this is also this term that differentiates the singlet from the triplet. You see, they have the singlet and triplet, they have everything else the same. They have the same non-interaction part and the same Coulombic repulsion part, but they differ in their exchange energy. And because the electron spins, they have a different configuration in these two states. For a very good approximation, we can say, let's say for the triplet, the energy is lower because the electrons, they have a parallel spin, right? But that's to approximation. And for the singlet state, we see the electron is raised, the energy is raised because we have extra energy corresponding to the pair electron. So once electrons appear, they have a more energy penalty in addition to the Coulombic repulsion, but also something relates to the pair, the spin. So we see those kind of terms have intrinsic origin in the quantum mechanics, and also in the property of the electron, because the electron have spin. So once they have a spin, the interaction between the electrons or between the spins will go into the final energy of the whole system. right? So this is something that we do not have a classical picture that we can draw analogy from, but by using this excited helium as an example, we can understand for the many electron systems, we have to deal with this kind of terms, the exchange energy, is exchange energy term. But this has some practical applications in our daily use of the chemistry knowledge, right? So exchange energy is basically saying parallel spins are encouraged, yeah, because they can bring a lower energy. We know the system always want to go to the lower energy. And one application is that either half or fully filled subshells would have substantial amount of extra stability. And this relates to the electron filling sequence we observe in the periodic table. So I take the example of chromium, for example, right? For the chromium, it have their 6 valence electrons. Then the 6 valence electrons has to decide which orbitals they want to fill first. We know we have the 3D and have the 4s. So if you look at the previous case, you may say, okay, so it seems like this 4s is the lower energy orbital because they always first fill the 4s and then fill the 3D, right? If we look at from titanium, from vanadium, it first fill the first 4s, and now we have a 2 in the 3D, and then we continue to fill the 3D. That's kind of indication saying the 4s has lower energy than the 3D. But when it comes to the chromium, we do not fill the 4s first. We do not actually have a full filling of the 4s. Instead, we have a half filling of the 3D using 5 electrons, because this kind of configuration brings an extra stabilization energy for the whole system. And this is the configuration it adopts. And also something similar happens to elements going down the periodic table. So I believe we have the ruthenium below the chromium, and you can also check similar cases happen for that element. Because once we have the subshell filled, there's extra stability. Also, it relates to the low spin or high spin.
Sorry to interrupt. Can I ask a quick question?
Sure.
So it is about this chromium electronic configuration. So I can understand that the electron goes to the d orbital first because it has the greater stabilization effect. So when we have the 5 electrons in the d orbitals, it is half filled. So the next electron, instead of going to the d orbital, it goes to the s orbital. Is it because of the exchange energy?
You can, at least you can think about in this way. First of all, 3D and 4S, the energy difference, they're not that different, right? They do not have a much different energy. They do not differ that much in energy. So in some cases, the 4S may be a little bit higher than 3D. In some cases, it could be a little lower. So the difference is not small. This is important because with regard to your question, if there are 6 electrons, choose go to the 3D, then it has to pair with one of their presenting electrons, right? In other words, electron pairs has to form. And we know, also learn from the previous slides, once you have electron pairing, then you have additional energy cost, not just to the Coulombic their repulsion, because now you have a pairing electron, they can occupy the same orbital, right? Because they can have everything the same, only the spin are different, and they can occupy the same orbital, and that increase the likelihood they will meet each other in the space, and that translates into a great increase in the repulsion also. So normally electrons always want to avoid pairing, right? Unless they have no other way to go, they have to do the pairing. So, and in the case of chromium, apparently that's not something electron want to do. Instead of going to the 4s, if it chooses to pair with some of the 3D electrons already there, this will increase energy quite a lot compared if just to go to the 4s. The 4s might be a little bit higher than 3D, but if I choose to go to 4s, the energy penalty is not that high compared, with my other option of pairing with the 3D electrons.
I see. Makes sense. Thank you.
Okay. But what you asked, I think, is just what I want to talk in the second part. So that's basically just the low spin or high spin decision. So let's take the example of the 3D4, right? So if we have a 3D4 cation, then we can reasonably argue that the first 3D electrons will go to the T2G, since they are the lowest level, right? So now the first electron has to make a decision. Should I go to the EG level, or should I go to pair with one of their T2G electrons? And the electrons, they're smart. They make the calculation before they, make decision. They can realize, how much energy will be associated if I go the pairing solution. If I want to pair with one of the 3D electrons, then the penalty is that, we have to sit together in the same space. There are a lot of repulsion between us. Yeah, even though I do not have to choose a higher level energy, which is EG. So electrons calculate that. Instead, if I go to the EG orbital, even though I chose an orbital with high energy, right? So actually the energy is raised, but I avoided a pairing with current electrons. So I have more space to move around. And that's my way of lowering the energy. If you choose the first one, pairing with the available electrons, then you are choosing low spin configuration, right? Because now you have a paired spin, then you are decrease the total spin of the whole system, right? So that's why it's called the low spin configuration. Instead, if you realize that it's just not worth it to do the pairing, instead, I'd rather go to the high energy level such that I can avoid the pairing, and that's the high spin configuration. Because now you have all the parallel spin, right? So that's why, and the total spin number is high. That's why it's called the high spin configuration. For the oxide systems, most of the transition metals would adopt a high spin configuration. And the reason is, oxygen is not able to create a very large crystal field splitting energy, such that the transition metals, they would rather go to the high energy level rather than pairing. And also this relates to the localizing nature of the 3D electrons. So transition metal oxides, most of cases would go to the high spin, but cobalt is an exception. And cobalt may not be the only one element, but probably the few elements in oxides that choose to adopt a low spin configuration. And this has a lot of fundamental implication on the battery materials. And there's huge momentum to go beyond the no cobalt, but why people have to start with cobalt in the first place? Because cobalt is exceptionally stabilized in the octahedral site. So lithium cobalt oxide has a perfect layer structure. It has no cation mixing at all. The cobalt is happily sitting in the octahedral site because the cobalt adopts the low spin configuration. All the 3D electrons, so cobalt 3+ is a 3D6. So all the 3D electrons, they're sitting in the T2G. So that's contributing a lot of stabilization energy. And the cobalt is very happy with octahedral. It has no tendency, no motivation to move around. So that's why cobalt is so unique for the layer material.
Yeah, so I just wanted to say something regarding that. So is it possible, like, if we can dope with a certain ligand to enhance the crystal field splitting energy so that we can promote more of the formation of those low spin transition metal ions? Yeah,
that's a good point. I think in the past, there were also efforts in that direction. But practically, the tricky part is, if you dope something, with too small amount, it may not have an obvious effect. But once you introduce more of those kind of foreign entities, then you probably would not able to, still have the same structure as you started with. You may change the whole structure, right? So, but I think there's some efforts to do that. For example, going from oxygen to fluorine, even though they both are kind of regarded as a weak ligand, but still oxygen and the fluorine has some kind of a difference. And by having fluorine substitution, you may have some, change to the behavior to the transition metal. But personally, I do not think that you can do too much about that, because that still relates to the, the chemical range that you can maintain this structure. Because for battery materials, especially for intercalation battery materials, we still need to maintain the structure. The framework cannot be changed, right? Everything has to be modified based on this framework. But if you introduce too much foreign cations or foreign molecules, you may change the framework.
I see. Yep, makes sense.
Yeah, yeah, and that concludes my talk today. Yeah, if you have any questions, please ask.
I have a question as well. Thank you for the presentation. And also you went into the singlet and triplet states. I'm wondering if you could elaborate on what the singlet and triplet states are. Yeah, I noticed all the
This one?
Yeah, what are singlet and triplet states? What are those?
The singlet simply means the degeneracy, or in a more general term, the degeneracy meaning that once you have the different configurations, but they turn out to have the same energy. So it's just the, yeah. So that's kind of the definition of degeneracy. So you see for the triplet, right? We can have 4 possible situations, 4 possible configurations, but they turn out to have the same energy. And what that means practically is that in the spectrum, you would observe only one peak, right? Because in the spectrum, what you really observe is only the energy difference. And because now you have the same energy for the ground state, and now if you have the same energy for this kind of a triplet excited states, then you only observe one energy transition, and that appears as one peak in the spectrum.
Okay, thank you.
Yeah, but as I mentioned, I made a mistake in drawing this, but I think you all understand that this should be the upside down, right? This should be rotated 180 degrees.
Yeah, I have one question follow up by this discussion. So we have singlet and triplet state because it's only 2 electrons, but in normal materials we have a lot more. I wonder, is there a general more like approximation to determine how many peaks we will detect, or it follows strictly for just like the case we discussed here that we only have like 1 peak?
Yeah, that's a very good question, and also that's something I'm planning to present for the next lecture. I touched some of this in the lecture on term symbol. I don't know, maybe some of you attended that lecture because that happened maybe 1 year ago or something. So in the spectroscopy, and people will use the term symbol to really to simplify, all those kind of possible configurations. So the challenge really comes from, you need to find a multi-electron wave function that really satisfies the Schrodinger equation, right? That at least there should be a solution that makes physical sense. It maybe it's not exact solution, but at least it makes physical sense and should be a good approximation. But even that is not simple. And people over the years, people have already derived ways to address this, and that is addressed in the term symbol. When you probably sometimes will see some kind of symbol like A1S something. Those kind of symbol are describing the states. So I hope we have a lot of our concept transition. Let's move from orbital to wave function and then to states, right? We have been talking about orbital all the time, but we know that the real answer should be the function. And in a more general sense, it's actually the state. It could be a little bit complicated combination of the wave functions, but has the closest correlation with what you observe in the spectrum. So for the transition metal LH, that's a typical system that many electron effect has to be considered. So maybe for a simple, like a 2 electron system, you would definitely observe more than 2 peaks if we talk about LH. And there people have ways to calculate those term symbols, and there we can discuss more in the future lecture. Yeah.
Thank you.
But also I want to mention that do not be too much bothered by the main electron system, because when we talk about the KH, either the transition metal KH or the oxygen KH, we still use the 1 electron picture quite a lot. And in the paper, if you describe in that way, and chances are, they were unlikely to raise objections to them, because people have been using 1 electron picture for their transition metal KH and oxygen KH conventional. But it definitely would fail if you go to the transition metal LH. The reason is that because in LH, you now have the 2p hole, right? Because exciting from the 2p to the 3D. Now you have a 2p hole, and you have an extra valence in the 3D. And in terms of wave function, this 2p and the 3D, they have a strong correlation, such that they cannot be treated separately. And that's the main reason that the 1 electron picture fail for transition metal LH, but you still can use that for the KH, either the oxygen or the transition metal KH. Yeah. Okay. Yeah. Any more questions? Yeah. Also, yeah. If you have suggestions, please feel free to ask, because I'm also exploring. Right. I've never teach this kind of lectures. I never gave this kind of presentation before. So I also want to balance the complexity and how practical it is. So if you have comments and saying some part probably needs more explanation, then we should discuss it. Or you think some part is maybe too abstract, not much related to what we do the research, we can be concise about that in the future.